Imagine you're traveling to another star. A meteor flies towards you at close to the speed of light. What do you do? What do you do?
Hi, I'm Jeff Friedman, and welcome to Sci-NoFi, Engineering Year 3000, where I describe practical solutions to future technologies. I'm a space sector entrepreneur with a PhD and more than 30 patents. Last December 2025, I sold my 2 companies, and now I write sci-fi novels and make videos like this one.
Sci-NoFi, Engineering Year 3000, Episode 1, on interstellar travel. How to survive near speed of light meteors. Traveling to another solar system would be really cool, but I'd rather not have to freeze my kids in carbonite for the 100-year voyage. Physicists will tell you that because of relativity, you could travel 100,000 light years across the Milky Way in a little over 20 years. You could even travel 2.5 million light years to the Andromeda Galaxy in about 30 years, because near light speed travel slows down time from the passenger's perspective. However, practical limitations will likely make those journeys impossible. A more manageable distance of, say, 20 light years, traveling in 6 years, is incredibly challenging, but might be possible. For an Earth observer, it will, of course, take longer than 20 years. But this means that it's possible one day to travel vast distances in our lifetime. And there are around 100 stars within that range that we could visit. To travel 20 light years, we'd need to accelerate at 1g for half the voyage until we reached 99.6% of light speed. Then we decelerate at 1g for the remainder of the voyage. We'd have the equivalent of Earth's gravity for the entire trip. But even if we could build a capable propulsion engine, 99.6% of light speed is insanely hazardous. An interstellar wind will light up the front of your spacecraft like an Apollo re-entry vehicle, and a speck of dust will destroy your ship. I'd first recommend placing a giant mass in front of your craft to block the deadly interstellar headwind. But even with that protection, you won't get far unless you can avoid meteors. At near light speed, a tiny pebble will hit you with the energy of a nuclear bomb. And light is only slightly faster than the rock flying toward you. If we give ourselves 1 second to dodge the stone, that at 99.6% of light speed, we have to spot that rock 250 light seconds away, or about half the distance from Earth to the Sun. So now we have a rock barreling toward us at close to the speed of light. It's tiny. It's 45 million miles away, and we have 1 second to spot it and dodge it. The rock is cold, tiny, and distant. A telescope can't see it, and radar can't detect it. Sounds impossible, but it's not. There's a solution. I call it GeMAS, the Geyser Meteor Avoidance System. And here's how it works. For this example, we'll examine a snapshot of our journey when we're traveling at 99.6% of light speed, and we're accelerating toward our destination at 1g. GeMAS fires a long, narrow particle stream ahead of your ship at 750 miles per second. At that speed, the stream reaches its apex 45 million miles in front of the ship. And that's because our spacecraft is continually accelerating, and the particles fall back toward the ship like a geyser. Acceleration acts like gravity. It's the same feeling you get when you hit your car's accelerator and your body pushes against the back of the seat. That acceleration forces the particle stream to fall back toward the spacecraft, as if there was gravity there. The GeMAS concept is simple. Meteors crossing our path collide with the top of the geyser. Geyser particles heat the rocks until either they vaporize or glow bright enough for us to spot. We'll need a sensor to detect a hot rock, but we already know how to do that as long as the rock is hot enough. And the geyser has to be wide enough at the top to catch any meteors that still might hit us after passing through. A meteor traveling 20 miles per second can move 5,000 miles sideways in the 250 seconds it takes for light to reach us. So our geyser needs to be at least twice that, or 10,000 miles wide at the top. We have 3 knobs to control the geyser's shape: how fast we fire the particles, how hot they are, and what they're made of. The faster we fire them, the taller the geyser gets. As particles shoot into the vacuum of space, they naturally expand outwards, and the hotter and lighter they are, the faster they spread. Together, these knobs let us control the height and width of the geyser at the top precisely. And the geyser we need is enormous. At 99.6% of light speed, it's about 45 million miles tall and around 10,000 miles in diameter at the top. Because of that mass volume, the particles are spread incredibly thin, 100 quintillion times thinner than our atmosphere. That's a 1 with 20 zeros after it. But at near light speed, even that trace artificial atmosphere is enough to protect the ship, because each one of those molecules slams into the incoming rock with tremendous energy. And that's because energy is equal to the speed of light squared multiplied by a relativistic parameter called the Lorentz factor. In this case, it's about 11. Together, this more than overcomes the geyser's vanishingly thin density. At 99.6% of light speed, the geyser blasts a marble-sized rock with 1/4 megawatt of power. Dust and micrometeoroids vaporize into mile-wide gas clouds, and larger meteoroids glow with a blinding light that reaches our telescope a full second before impact, giving us just enough time to fire thrusters and dodge. This general approach works for any velocity up to 99.9% of light speed, but at different speeds we'll have to adjust the geyser's height and width. So, for the first half of our voyage, we now have an effective method for both meteor destruction and meteor avoidance. But what do we do when we're decelerating? We can't make a forward-firing geyser while the ship is slowing down. Instead, every 12 hours or so, GeMAS shuts down deceleration and the ship coasts. Particles are released into a massive cloud surrounding the ship. Then, when the craft restarts its deceleration, the cloud falls away out of the front of the ship. We repeat this cycle, and then a series of clouds leaves the ship and protects it on the entire way there. GeMAS then detects and dodges any meteors that collide with the cloud, exactly like the forward geyser, just in cloud form. To implement the system, you'll need to haul additional mass for all of those particles in the geyser, as well as the fuel required to propel those geyser particles. The good news is that extra mass burden is fixed, so larger ships will require a lower percentage of additional mass. So now our spacecraft has 2 protections. First is a giant mass shield to protect against the constant interstellar headwind, and 2, GeMAS for meteors that the shield can't stop. Meteor avoidance isn't the greatest challenge for interstellar travel. My next video is on the deadly interstellar headwind. What is it? How intense is it? And how do we keep that giant mass that's in front of the ship from vaporizing when the interstellar wind cooks it? Subscribe so you don't miss a thing. If you want the full GeMAS equations and design details, read the technical appendix of my new hard sci-fi novel, Flight of the Medusa. For a free copy, click on the link below.